All right. Today, September 11th, 2020. All right. Where we stopped last time, I think we were talking about a theorem, right? Here, properties of invertible matrices. So the first one, we have already proved the three of them. We will continue from here today. The first one, it says that if A is an invertible matrix, then A inverse is invertible. Right? That's A inverse equals A. We have already proved this. And B, if A is an invertible matrix, then C is a non-zero scalar. And C times A is an invertible matrix. And here we have 1 over C. C times A inverse equals 1 over C times A inverse. And also C, if A and B are invertible matrices of the same side, it's like transpose, and AB is invertible, and AB inverse equals B inverse times A inverse. Okay, we have already proved this stuff, and these are the proof, and let's continue from here. In part D, it says that if A is an invertible matrix, so what color here we have? Let me choose this purple. So when we just say invertible, immediately you have to think or imagine this relationship, right? It has inverse, and A times A inverse, that's equal to I. It means this. So if A is invertible matrix and A transpose is invertible, and A transpose inverse equals this. So again, I have to show here that A transpose inverse equals A inverse transpose. What does it mean? So that means that if I multiply this thing, right, by it is inverse, so it should be equal to, what is it? It should be equal to I. Anyway, here, because here the inverse, we are trying to find this is inverse. Let's say its inverse is X. So the inverse of this matrix, okay. Since it is inverse is X, I have to find X. So when I multiply A transpose by it is inverse, it should be equal to I. So from here, how can we actually eliminate this thing? In other way, I can just write it as this. This one is, what is it? A transpose, all right. Okay. So X transpose. Okay. So here we have X equals, because multiplying both sides by its inverse, we will have something like this. A transpose inverse times X equals A transpose inverse. Here we have A transpose, and here we have X, and I just multiply both sides by this, so here we have A transpose inverse. Now from here, A transpose inverse and A transpose, here we have matrix B inverse, matrix B, so that's equal to I. So here we have I times X equals A transpose inverse. So what is X? Here we have X equals A transpose inverse, right? So we have to show that actually that's equal to that thing. Right now, A transpose, I had to show that here that's equal to A transpose inverse. So if I can show that this A transpose inverse, okay, times that is X, and here we have A transpose. So that's equal to, we know that it's equal to I. In other way, I can just write it as, because if I just keep this, why am I confused here? Okay. So here, A transpose inverse equals A inverse transpose. So we are saying that A transpose inverse equals this. So that means that I have to show that A transpose this matrix and its inverse is A inverse transpose. And we have to show that that's equal to I. I think this way is much better. Let's just put it in this way. Sometimes using a lot of notation, so it might be a bit confusing. So we have to show that still I'm not sure it is true or not. Okay, I have to show that that's equal to I. If it is true, that means that this matrix A transpose inverse, that will be equal to this because your product is equal to I. Because we know that from the definition, if A times B is equal to I, that means that A is the inverse of B or B is the inverse of A, right? And how do you know this? We actually know this with some B as the inverse of A. So in a similar way, by using the property of transpose, we know that if we have AB transpose, that's equal to B transpose, A transpose, right? And here we have B transpose, A transpose, so I can just write it as A inverse times A, that's the first matrix, this is the second one, and here we have transpose. And that's equal to A inverse A, that's equal to I transpose, and it's just our identity matrix that's equal to I. So that means that A transpose inverse that's equal to A inverse transpose. In a similar way, this is D, this is E. If A is an invertible matrix, the last one, then AN is also invertible for all non-negative integers n. And A to the power n minus 1 equals, actually not minus 1, it's inverse equals A inverse n. It's actually that generalization of part C. In part C, what we proved, we already proved that A times B inverse, that's equal to B inverse A inverse, right? And in a similar way, if we have A, B, C, for example, here, if we have A, B, C, inverse, that's equal to C inverse, B inverse, A inverse. In general, if we have n matrices here, for example, in general, that's a special case. However, if we have A1, A2, dot, 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 AN, and here we have inverse, that's equal to AN. We are just writing this in reverse order. And the previous one, and here we have A2 inverse and A1 inverse. Okay. Maybe by using mathematical induction, we can prove this in some different way by grouping. For example, if we have A, B, C, you can just consider this one as one matrix, let's say D matrix, and after that, open the brackets, and after that, instead of D, write BC again. In this way, actually applying this rule again and again, we can prove this, or also by using mathematical induction. Anyway, guys, these are the properties of matrices, and that's the general case that we already did this. So in this way now, we can introduce that negative power. That negative power, actually, when we just write this, A to the power minus m, right? What do we mean by this? We mean A inverse is raised to the power of n. Or that is the same thing as first raise A matrix A to the power of n, and after that raise to the power of negative 1. And immediately we can have these properties, so A to the power m times A to the power n. But here, notice that actually these matrices are the same. A to the power of m plus m. It's very similar to real numbers, exponents. A to the power m to the power of n, that's equal to A to the power of m times n. Easy to remember. Okay. Let's immediately do one example. As we know that when we are solving this kind of equations, always keep in mind that A times B is not equal to B times A. Number one, when you're just solving this kind of equations. Number two is, we know that A inverse, that's equal to A inverse A, that's equal to I. Okay. So here, solve the following matrix equations for capital X, assuming that the matrices involved are such that all of the indicated operations are defined. And this example is just to, how to say, for a warm up and get used to using these matrices. They are not just real numbers. So here, to solve the for x, that means that we need to actually leave this x alone on the left hand side and take everything to the right hand side. How? By using those properties, right? So first here, maybe I want to eliminate this a. How can I do that? If you just multiply both sides by the inverse of a on the right, what we have here, a squared. Okay, I need to wear my glasses. A squared, and here we have x, and here we have ba. Sorry, also actually I need to multiply a inverse because I'm eliminating a. So here we have ab. Since I multiplied on the left, on the right, so also I need to write here a inverse. Now immediately, if you simplify here, a inverse is equal to I. So here we have b left. And also a inverse, I have nothing to do with this because between this a and a inverse, we have b. Now I need to eliminate this b. So I multiply both sides by b inverse on the right. So here we have a squared x, and here we have b. This a inverse is gone. So here we have b inverse. How about here, a inverse, and b inverse. Maybe I can just write it as b a inverse. And now bb inverse is gone. Now actually I need to eliminate this a squared. How can I do that? We should multiply both sides by a to the power minus 2. It's a squared, right? And here we have x. So here we have a to the power minus 2. A, here we have b, a to the power of negative 1, b to the power of negative 1. Now, negative 2 plus 2, because the same matrix, we should just add their exponents, right? That's equal to power 0. I mean, a to the power 0 is I. So here we have x left. That is the last answer, actually. And here, if you simplify this, here we have a inverse. Here we have b, and here we have, I can just write it as a inverse b, a inverse, b inverse. Okay. And also, of course, in a different way. For example, if I just write all together in reverse order, I can just write it b, and here we have a, and here we have b inverse, here we have a, and here we have inverse. Okay, that thing is equal to, what is it? X. And how about part B? For part B, let's use a bit different color. In a similar way, so we need to leave x here, right? So first I should multiply both sides by a on the left to eliminate this a. When we do so, here we have a inverse. So here we have bx inverse. On the right, here we have a, and here we have a inverse b cubed, and here we have 2. But here you should be careful. Here we have ab squared is not equal to a squared b squared, right? And by the definition here, what is ab squared? ab squared means ab is multiplied by ab. Okay, that is the thing. You should be careful. AB, back maybe for real numbers, it's true, but for matrices, this thing is not true. We don't have such property, and we have never seen such thing. AB squared means AB times AB. So just keeping this in mind, AA inverse is equal to identity matrix, and if you just expand this, here we will have X inverse, and here we have B inverse. On the right hand side, I have A, let me just keep it as it is, A inverse, B cubed, and here we have squared. So now I should multiply both sides by B, right, to eliminate this thing. So here we will have A inverse equals A inverse, and here we have B cubed squared. On the right, here we have B. So actually we need to find X. How can I find X? If you just raise to the power of -1, right, both sides, then I'll have here A, here we will have A A inverse B cubed squared, and here we have B, and that's equal, and here we have -1. If you want, you can just remove this, or we can just leave it like this. This is how we solve this kind of matrix equations. And of course, here we're just practicing that this thing, actually AB squared is not equal to A squared B squared, and practicing some of these properties. So let's move on. Now we will talk about elementary matrices. Okay. Actually, it should be before this. All right. So now we are going to use matrix multiplication to take a different perspective, different approach on the row reduction of matrices. Right? As you know, if you remember, when we want to, like, when you are solving algebraic equation, we have to simplify, right? We need to, by using some manipulation, and after that we can solve the equation. Or for matrices also, when we are simplifying this, right, we are allowed to do, what is this, 3 basic operations. We call them elementary row operations. What are these? We can just interchange 2 rows, or we can multiply a row by a constant number, non-zero constant number, or we can just multiply a row by a constant and add it to another row. These are elementary row operations. We are saying row operations because we are doing these operations on the rows of the matrix, not on the columns. So here, in this process, you will discover many new and important insights into the nature of invertible matrices. Here we are going to get introduced with elementary matrices. If we just start with considering these examples, assume that here we are given matrix A, right? 1, 0, 0, 0, 0, 1, 0, 1, 0. And A, that is 3 by 2 matrix, 5, 7, that's first row, the second row, -1, 0, third row, A, 3. And the first thing is, if you notice here, what is this A, right? And if I just write identity matrix here, here we have 1, 0, 0, 0, 1, 0, 0, 0, 1, right? If I just switch, or if I just interchange the second row and third row, right? If I just do this operation on this matrix, what do we have here? I get this E here, right? Just 2 second and third row is interchanged, and those rows are interchanged. And if I just multiply these two matrices, you can just multiply it and see that 5 times 1, -1 times 0, 0, 0. So 5 and 7 is no problem. But when we just multiply this, we will have this matrix, E times A equals this. And what is the difference here? Like, what difference we see here? As you see here, since I obtained this matrix by interchanging the second and third rows of identity matrix here, right? If I just multiply this by A on the left, actually, the result is the same as just interchanging the second and third rows of this matrix, right? So what does it mean? It means that actually just interchanging the second and third row actually is the same as multiplying this A by these matrix. Now we're just going to give a special name to this. We call them elementary matrix. So what is an elementary matrix? It is any matrix that can be obtained by performing an elementary row operation on an identity matrix. Since there are 3 types of elementary row operations, there are 3 corresponding types of elementary matrices. Because we know that actually here, if you're given any, let's say A, B, C, D, right? Any matrix, right? And here we have identity matrix. Here we have 1, 0, 0, 1. Maybe in 2 we can oh, okay, it's fine. And how many elementary row operations I can apply on this? 3, right? The first one is we can interchange the first row with the second row. Let's say it's the first type. So here we will have 0, 1, 1 0. Just interchange this first and second. And third one is we can multiply either the first row or the second row or any row by a constant. If I multiply the second one by k, for example, we will have 1 0 0 k, right? And third one is how can I obtain another elementary matrix from this identity matrix? Let's say it's the third type, and I can just multiply either the first row by any constant, add to the second row, or multiply the second row by any constant and add to the first row. And let's just do this, multiply the first row by k and add it to the second row. So we will have here k1. These are all elementary matrices. In the definition, we are saying that an elementary matrix is any matrix that can be obtained by performing an elementary row operation. N means here 1, by applying only 1. Elementary row operation on an identity matrix, How many elementary row operations we have? Only 3. So we can obtain 3 different elementary matrices. Example. So these are the examples for elementary matrices. For example, this E1. How did we obtain this on I3? We just multiply, right, the second row by 5. 5 times R2. And how about this one? See here, this one should be here, right, in identity. If I just interchange this, for example, the first row and the second row, we will get identity matrix. Then how did we get this, obtain this elementary matrix? By interchanging the first row with the second row. And how about this one? If you notice here, this one is -3, right? That means that I should multiply the second row by -3. And if I add this to the third row, right? Yeah, because here we have identity matrix here. Here we have 1 0 0 0 1 0 0 0 1. So if I multiply the second row by -3 and add it to the third row, we will obtain this. So how do we obtain this elementary matrix? By multiplying the second row by -3 and adding this to the third row. This is how we obtain this. Actually, these are all elementary matrices. Okay. Now here, let's see the effects of these products. What is E1 times B here? For example, if you multiply this matrix E1 by B, what do we get here? See here, when we just multiply E1 by B, right? What is E1 by B? What is E1? E1 is just we multiply the second row by 5. And you will see that we will have the same effect. And maybe for the first one, you can just do this. Here we have 1 0 0 0 5 0, and here we have 0 0 1. And here we have the matrix A, B, C, D, and E and F. So if you multiply this, we know that we will have again 3 by 2 matrix, right? If you multiply the first row by the first column, all entries are 0 except the first one. So here we have A. Multiply the second column by this. So here we have B. Now multiply the second row by the first column. Here we have 5 times C. Here I have 5C. The second one, second row by the second column, 5 times C. So here we have 5D. And it's just 0 0 1. It's like standard unit vector, right? Here we will have E and F. Now, as you see here, what is the effect? It's just the same. What we are doing here is we just multiply the second row of B by 5, right? So actually, next time we don't have to do this. Always, actually, this is true. So what is the effect of this E1? How did you obtain this? Multiplying the second row by 5. So multiplying E1 by B, that means that just I need to multiply the second row of this B by 5. And in a similar way, how about E to B? So now E to B, what is the effect of E2 on B? Just we need to interchange the first row with the second row, right? That means that A, B, and C, that we have to interchange this things. So here we will have C, D, here we have A, B, and here we have E and F. And how about E, 3 and B? E3, as see here, we should multiply the second row by -3 and add it to the third row. So here we will have a bit longer one. Okay, here we have A, B, nothing to do with the first row, and C, D, also not to do with the second row. So we should multiply the second row by -3 and add it to the third row. So what do we have here? Here we have E minus 3 times, I should multiply by 3, right? And add to the third row, A. And I can actually write here a bit in some space. B, A, B. Here we have this one is D. Okay, here we have A, B, and C, D. And how about here? Here we'll have F minus 3D. Okay, right? This is the effect of elementary matrices. You will see that in the future, in a lot of cases, instead of multiplying this, writing in this form, actually, these chains in this form, we'll see it will be much practical and easy, and especially improving a lot of theorems, we will use this kind of product. Okay. All right. And we have another theorem that is the, what is it? Generalization of the previous operations. Let E be the elementary matrix obtained by performing an elementary row operation on IM. Now we know what we mean by elementary matrix, and we know actually that it produces the same effects when we just multiply elementary matrix by a matrix, right? If the same elementary row operations is performed on an n by r matrix A, the result is the same as the matrix EA. So if the same matrix row of elementary row operation here, I'm gonna say green, maybe I should use that's or not. So elementary row operations performed on n by r matrix A, the result is the same as EA. We have just seen this in examples. Find the inverse of the following elementary matrices. And also actual elementary matrices, they have inverses, and the inverses are of the same type. And we will see them as the theorem, okay? Because first one, for example, let's say E1, right? And you see here E1, just the second row is multiplied by 5, right? So how can I find it is inverse? 1, 0, 0, 0, 5, 0, and here we have 0, 0, 1. Okay, so to find it is inverse, how did I obtain this 5? By multiplying the second row by 5. Then it is inverse will be, its inverse will be 1, 0, 0, the same type, but here we multiply, so inverse will be here, we have 1 over 5, 0, and here we have 0, 0, 1. You see here, if you multiply them together, 1, 0, 0, right? And here, when we multiply this 5 by 1 over 5, then we will have here 1. So, in general, here if we have k, then its inverse, instead of k, here we must have 1 over k. The rest of the, what is it, entries or elements are the same. And how about this E2? E2, we just interchanged, right, the first and second row. So also it will be the same thing. It's just itself, the E2 interchanging the first all right, E2 inverse. Let me just write like this. So here we have 0, 1, 0, 1, 0, 0, 0, 0, 1. So also its inverse will be of the same type. That means that it will be exactly the same. Just we need to interchange these two rows. So it is 0, 1, 0, 1, 0, 0, 0, 0, 1. So see here, if you multiply this, 0 times 0, 0, 1 times 1, 0 times 0. So here we have 1. Multiply the second row, it is 0, 0, 0, 0, because it's in the middle. So in the middle, we don't have what is it? We don't have 1 here, so that's equal to 0. Also here, that's equal to 0. Now, if you multiply by the second row, 0 times 0, 0, 0. So here we have 0. And here, the first entry, that's 1, the rest is 0. And the last one, only here 0, others are, what is it? 0, 0, 0, and here we have 1. So it's exactly the same thing, actually, in the second type. How about the third one? Third one is, see here, this one, how did they obtain this matrix? We obtain this by multiplying the second row by -3 and adding to the third row, right? So it is inverse. How can I obtain its inverse then? So actually here we have multiplied by -3, right? So here actually multiplies by 3 and multiply by R2 and added to the third row. So that means that here we have E3 and E3 inverse. E3 is, here we have 1, 0, 0, 0, 1, 0, 0, -3, 0. I mean 1 here. Okay, now here we will have 1, 0, 0, 0, 1, 0, 0, 3, 0. Yeah, actually not 0, it's 1. So if you multiply this, for example, here the first one, 1, 1, no problem. And the rest is 0. And here we have 0. Second row, 0, 0, 0. So it is 0. And 1, 1. It is 1, it's 0. How about the third row? 1 times 0, 0, 0 times -3, 0, 0 times 1, 0. So here we have 0, no problem. 0 times 0, 0, 1 times -3, -3. 3 times 1, it is 3. So that's equal to 0. That's why they're saying this, it is also of the same type. But here, just if it is added, we should actually, if it is subtracted, right, we should add. If it is multiplied, we should divide. So, and the 0 times 0, okay, all are 0. So here we have 1 times 1, here we have 1. That's also identity matrix. That is how we actually find the inverses of elementary matrices. Okay. So now as a conclusion, we can just give this a theorem. Each elementary matrix is invertible, and its inverse is an elementary matrix of the same type as in the example, in the previous example. So we have 7 minutes left. The fundamental theorem of invertible matrix. Let's just start this one, and I will finish this session by this. So this theorem, fundamental theorem, as see here, by adding some new, let's say, properties, actually we will just make it bigger and bigger theorem, and we're going to actually see this very frequently. As we have new facts, we'll just add it, and we'll have this until the end of this book or this course. Okay. This theorem says that if A is an n by n matrix, that's a square matrix, the following statements are equivalent. So now, when we say just equivalent means, here, what we mean, if one is true, one of them is true. Here we have A, B, C, D, E. Five facts here we have. If one of them is true, then all of them must be true. If one of them is not true, it is false, then none of them is true, or all of them are false. This is what we mean by saying equivalence. Okay, so now we will establish the theorem by proving the circular chain of implication. Here, that means that I assume that A is true. If A is true, I will show that then B must be true. Now I have two facts, A is true, B is true. If these things are true, or any of them is true, I will prove that then C must be true. If C is true, then we will show that then D must be true. That if D is true, then E must be true. And if E is true, then A must be true. We mean some kind of, what is it, circular chain. We mean by this, okay? So once again, if one is true, everything must be true. If one is false, then all are false. So now I assume that A is true. And using this fact, we will show that B is true. And actually, we have already proved this B part. If you remember, AX equals B has a unique solution for every B, because since A is invertible, right, I can multiply both sides by its inverse, A inverse A. Here we have X. Okay, here we have X. And here on the right hand side, A inverse B. And from here, X equals A inverse B. And also, actually, we can show that, assume that Y is in a solution, we will get the same thing. That means that it is unique, right? So this is how we prove this. Okay, now also B is done. Now, the second part is, now I assume that B is true. If B is true, how can we show that also C is true, right? Assume that AX equals B has a unique solution for any B in Rn. For example, AX equals B, it has a unique solution. Okay, so if it's a unique solution, again from here, if I just form this equation, okay, because B can be anything, we don't have any restriction. I'm not saying that B is any kind of special vector here. So in particular, if it is zero vector, right, if you just multiply both sides by its inverse, A inverse A, X equals A inverse 0, from here X equals 0. And its unique solution, we are saying that it has unique solution because A is invertible. If A is invertible, AX equals B has a unique solution. And if I just take a special case, if B is equal to 0, still actually, it actually keeps this position here, so it has unique solution, and the solution is 0. So that means that what is 0? It's a trivial solution. Here we have not a single number, it's a 0 vector. Here we have all entries are, or is it 0? Okay, so that's done. So this is done, done, done. Now we have A is invertible, AX equals B has a unique solution for every B in Rn, and AX equals 0 has only the trivial solution. Now we need to show that the reduced row echelon form of A is IM. So we are assuming that AX equals 0 has only the trivial solution. What does it mean? Trivial solution means, let's see, I can show it here. That means that here we have something like this. Here we have x1, right? Dot, 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 because all are 0. And here we have 0, here we have x2, dot, dot, here we have 0, dot, dot, and here we have xn, that's equal to 0. Now, how can I write this one? I can just write it as, here we have identity matrix 1, 0, 0, 0, 1, and here we have 0, 0, 1, and here we have x1, x2, x3, and here on the right hand side, here we have 0, 0, 0, right? And what is this? That means that we had changed our system into this form, and which is an identity matrix here. That means that reduced row echelon form of A is IN, identity matrix. And E, it says that A is a product of elementary matrices. If we assume that the reduced row echelon form of A is IN, then A can be reduced to IN using a finite sequence of elementary row operations. And by theorem 3.10, each one of these elementary row operations can be achieved by left multiplying by an appropriate elementary matrix. If the appropriate sequence of elementary matrices, for example, let's say, okay, I can maybe write here, well, last one. If those actual bunch of this elementary matrices, let's say here we have E sub k minus 1 dot dot, here we have E sub k, E sub 1, and here we have the coefficient matrix, right, or augmented matrix on the right hand side, IN. That is actually, I'm using the fact D because the reduced row echelon form of A is IN. So that is I, right? We are just applying K elementary row operations, and then we have just converted this into IN. Now each one is, what is it? Invertible. From here, then I is just equal to the inverse of this thing. If you just multiply both sides by its inverse, here I have E sub k and E1, and here we have inverse, right? And just equal to, what is it? The product of elementary matrices. Okay, let's stop here and we'll continue after maybe 10 minutes.